Welcome back to Uncle Fish. This is part two of Programming Foundations. I want to apologize for how I ended part one. I wasn't quite sure how to end the video, so it kind of ended abruptly. I'll try to do better this time. Where we left off in part one was we were describing binary, basically, zeros and ones at the very lowest level, and how we can convert that to essentially numbers, and then how we can convert that to essentially characters, and essentially a language on top of that, right? Eventually. So, one of the things that we want to understand is at that lowest level, where we were just passing the zeros and the ones down to the electrical components, basically. There's a name for this. They call it machine code. And there's something very special about machine code, right? And the special thing about machine code is that it's really hard to read as a human being. You can't really reason about this. You can't tell, right, just by looking at it, what's this program doing, how it's doing it, right, or any of those kinds of things. And further, if you had a problem, where would you go look to fix it, right? Next to impossible here to kind of reason about these numbers. So we need something better, right? Especially if we want to write lots of programs, we need something better than this. So the level above this is something called assembly language. Again, the premise of what we're trying to do here, right, is we're trying to get the computer, the machine, to do something for us, right? To follow some sort of instructions. But we need to do it in a way, right, that where we can at least read it. And so that's what assembly language is doing for us. So it's absolutely more user friendly than um, binary, but it's not as user friendly as your higher level languages, which were built on top of assembly language. So the higher level languages are ones that you will see in school, right? When you see in your daily activities, if you're a computer science major, for example, and these are your C++s, your Javas, your Python, so on and so forth, right? Go, there's a whole slew of languages. And so, but what's happening here, right? So this one is absolutely user friendly because this is human readable. We'll give examples of these. But how do we get from here all the way to here? Because at the end of the day, what did we say we were doing, right? We are trying to get information to an electrical system, right? Something that understands zeros and ones. So keep this in mind, right? That as you're going from these different layers, that eventually you're going to get to this machine code layer. And along the way, you need some help. You're going to need some translators along the way that are going to convert what you've written here into this and then convert from here into here or from here directly to here, right? Depending on the language. So just keep those things in mind as we move forward. So we are trying to learn at this level, right? But don't take for granted that there are teams and jobs that are operating at this level and things that are operating at this level, right? That are writing the instruction set. And there's others, like I said, like microcode level, like the CPU that we're not going to discuss here. But I think one of the key things is to always respect the complexity, right? That's there and the things that people have done to make life easier for some of the higher level language developers. Right? So now, with that said, again, at the end of the day, what are we doing? We're trying to write instructions, right? We're trying to write instructions to a component of the machine to do something for us. Well, what is that component that we're trying to write instructions for? That component is the CPU, the central processing unit. This is what is the brains of the computer. We'll write that down. I apologize for my bad handwriting. And this central processing unit not only is processing those instructions, it has a lot of subcomponents that it's made up of. We will not go into all of the details, but just again to get yourself familiar with things, there are things like registers, there are things like L1, L2 cache, super fast like storage basically for the CPU to be able to move things around and do some operations like arithmetic against it. That's what the ALU subcomponent, for example, is doing. So lots of different components in here. There's a component that manages memory, and again, several other things. So these components are then used to follow some instructions, to do some instructions. And they may then go interact with other components inside of the system. They may interact with volatile storage, short-term storage like memory. They may talk to hard disks for permanent storage, for example. Whoops. Right? They may talk to your video, to your screen, basically, right? So your video or screen. They may talk to other I/O devices, your keyboard, your mouse, right? Any of these types of things. And again, there's other complexity here, like operating systems and hardware abstraction layers that we're not focusing so much on because our focus really is about how do we get a programming language to interact with this. So knowing this, right? Knowing that what we are doing at the end of the day is to try to give instructions to this particular component, let's go take a look at something in assembly to illustrate just how that might look, right? So what I did is I went to GenAI and I asked it to write a program to just simply add 1 + 1 in, for a given CPU. So if you look again, as I mentioned earlier, this is more user-friendly than binary for sure, right? But it's not really that user-friendly. We're talking 1 + 1 here, and there's at least 15 different lines of code, right, to get that to run. But let's spend a little bit of time on this. So the assembly is broken up into different sections. So like the BSS section, for example, this is for storing variables. You'll have a section specifically about where the program is in text. There's a global variable that says, hey, this is where I want to go to start the program. And so now the beginning of the instructions are here. And this really simple concept about where to start is so often misunderstood by the students that I have that are in computer science and programming. They know they have to write a main argument. They know they do it in C++. They know they do it in Java, for example, but they don't really know why they're doing it, right? This is why you're doing it. You have to be able to interact, right, at the machine level, eventually getting to, for example, assembly, then to machine. But you have to be able to go tell it, this is where I want you to start the instruction. It's like you're giving someone a recipe to do something. Here's what I want you to do to start with, right? So what do we want to do? We want to move into this register called EAX, load the number 1. We want to add 1 to whatever's in that register, right? We want to store that result in some variable that we named up here, right? We want to print that result to the screen. And so now you see it's interacting with other pieces. The kernel is in the operating system, right? STD out. These are things that are going to go right to the screen, for example. So there's all of this stuff happening just to add 1 + 1. And there are teams of people, absolutely, and companies that are developing in assembly. But the fundamentals here that we're talking about is at the higher level languages, right? So these are the instructions, and you can hopefully see that we are literally writing instructions to the CPU and telling it, I want you to do this, literally move it from this register to that register and do something with it. So it's pretty complicated stuff in my opinion, right? And again, you're going to need some level of translators that are then taking this and turning it into binary, 1s and 0s. And you're going to need another level of translation, for example, that took the higher level language that you and I wrote into this. Okay? So one of the things before we get into, what are those languages and how do those languages function and such, we need to think about what language do these CPUs speak themselves? Do all of them speak the same language, right? Do they all honor the same instruction set? Do they all look like what I just showed you in that assembly? And the answer, fortunately or unfortunately, depending on your vantage point, is no, they don't, right? There are different types of CPUs. There are RISC-based CPUs. There are CISC-based CPUs. This is complex instruction set. This is reduced instruction set. Different companies use the different architectures. For example, like a RISC-based was your Unix-based systems like Solaris, AIX, those that likely most people haven't even heard of these days. But like ARM, which is advanced RISC, this is stuff that like Apple, for example, uses, or at least uses now. The CISC is used by Intel, for example, and AMD as their instruction set. So that's great, but what does that really mean for programming? What does that have to do with us, right? Well, it's important here because when we're talking about those translators that we talked about earlier, right? Let me just put this in case people are reading it. So when we talk about those translators, we got to know what language we're translating to, right? So we took our higher level language, like C++, okay? And then we had to convert this somehow, right, into something that this would understand. So this is called compiling or compilation, right? So if I am compiling my C++, I'm actually compiling it into machine code, right? So it compiles into machine code, which again, that's the zeros and the ones, right, that we talked about. But of which instruction? Would a RISC-based computer or CPU be able to understand that? And the complex instruction set computer? And the answer is no, right? The answer is no because this has its own instruction set, this has its own instruction set. So for languages like C++, where you were compiling it down to the machine code, well, you had to have two versions of it. If you wanted that program to run in this CPU, right, CISC, and in this CPU. Simple example, meaning like if I wrote something on Intel and compiled it on Intel, I can't just take that program, if it was C++, and just go run it on a RISC-based system. It doesn't work like that, okay? And so it's super important to understand this because what ends up happening after this is that, and for good reason, is you start to see the advent of interpreted languages, which we're going to go talk about in the next section, right? As to what is the difference between compiled and interpreted and so on. But the main point here is to understand what exactly we're writing. How do we get those translators implemented? What is the assembly language that we're talking about here, right? What are the start pieces of those things? And at the end of the day, we're writing instructions. And those instructions end up being very low level operations at a hardware level. And if we don't understand that, then when we talk about performance and we talk about other things at that lower level, those subject matters become extremely complicated and often misunderstood. Okay? The last point that I want to point out, I just don't want to gloss over it here, is we are grossly oversimplifying, right, what's happening at the hardware layer. There are logic gates, there are all sorts of other things that are happening there to be able to implement some of those, the things that we can do in those higher level languages. It's not just as simple as the CPU. But we're doing that by design, right? Like this is again to try to build a good foundation so that we can start to code on top of that. Okay, thanks so much for listening and tune in for Programming Foundations Part 3, which is again going to talk about the different languages that we have. Thanks.